So let's start. So in this week we'll be mainly looking at diffusion model, and we will look at the dielectric relaxation time, finite difference methods, normalization, scaling, linearization, Poisson's equation, Carpenter-Gummel discretization of the continuity equation. So before going into the questions, so just a recap, this is the drift diffusion model. These are the key governing equations of the drift diffusion model. The first one is the charge neutrality or charge density equation. Second one is the Poisson's equation, where the derivative of electric field with respect to position is rho by epsilon. This is the well-known Poisson equation that we have solved earlier also. These are the carrier density equations. N equals to Ni e to the power E minus Ef by Kt. Similarly, P equal to Ni e to the power Ef minus E by Kt. And the current density equation, Jn is equals to Nq mu E plus Q dn by dx, where this is the here this is the drift part, which is due to the electric field. This is the diffusion part. Yes. Yes, you are audible. Is it audible now? Hello, am I audible now? Okay. So yeah, we had just started. We were revising the drift diffusion model. So drift diffusion model, these are the following equations that govern the drift diffusion model. This is the charge neutrality equation. This is the Poisson's equation. These are charge density equation. We have seen them many times. Here psi, q psi is simply E, and q phi n is Ef. This is the current density equation, where the first part is the drift part and q mu E, and the second part is the diffusion part. So if you look at the videos in the derivation, we get this by certain assumptions in the Boltzmann transfer equation and with the Fermi-Dirac statistics. Okay, so these are just the continuity equations. Continuity equation is dn by dt equals to 1 by q del j by del x plus g minus r. Here they have taken the SRH recombination, so they have substituted the R recombination rate in SRH with this part. Okay, so now let's go to the questions. I think this brief is enough. The first question is, which type of recombination is dominant in indirect bandgap semiconductors? No. Why do you say radiative recombination? Okay, so okay, so then why will it be radiative? What? I'm sorry, I don't understand what you're saying. Yeah. Hmm. What will it radiate? So radiative recombination always takes place in direct bandgap semiconductor. Yes, yes. So these indirect bandgap emitters are like silicon. Silicon we never have radiative recombination. So in these kind of materials we have SRH recombination, which is also known as trap assisted recombination. So as you said, what happens is first the electrons reach to some trap state, then they recombine. So it takes place in multiple steps with the help of trap states. So this is the dominant recombination in indirect bandgap. So next question is, which type of recombination is dominant in direct bandgap? Right. In direct bandgap semiconductors, there is no other energy loss. You directly there is a recombination from conduction band to valence band and it radiates photon. An example of this is gallium arsenide. Okay, next question. Which of the following statements is not an assumption made in drift diffusion model? Yes. It is temperature gradient is considered. This is the incorrect assumption. So if you remember the video, the assumption that are made in the diffusion model are it is first is full ionization, that is shallow dopant. That means the energy level between EC and ED is very small, much less than room thermal energy. It is non-degenerate. Non-degenerate means its minimum distance is still between EC and EF is more than 3 kT. Steady state means near equilibrium condition. And isothermal, that means temperature is constant across the whole semiconductor. So this is an assumption and this is incorrect. Okay, let's look at the next one. Which of the following correctly describes the physical significance of Debye length? Yes. So Debye length corresponds to screening, and in this at Debye length the electric potential decreases by a factor of E. And if we see the lecture video, this is the formulation for Debye length. LD Okay, next question. Consider a semiconductor doped with pentavalent impurities of 10 to the power 17 per centimeter cube. Calculate Debye length. Okay, solve it. So d by length LD is under root epsilon Vt by Q max dou, which is 11.8 into 8.854 10 to the power minus 14 into 0.026 divided by 1.6 into 10 to the power minus 19 10 to the power 70. You solve this, you will get 13 into 10 to the power minus 7 centimeter, which is 13 nanometer. Please check your answer. It should be 13. I have calculated. What value have Vt have you taken? Then it must come to this value. Okay. Okay, so next question. Why the dielectric relaxation time is important in semiconductor device equations? It is option C. And what is relaxation time? So it affects the time that is taken by the majority carriers to respond to the changes in electric field. We can derive this if we consider the what is this? This is the continuity equation. That is del n by del t is equals to minus 1 by q del j by del x plus g minus r. If there is no recombination and generation, these two terms will be 0. And current current density Jn can be written like this. And if there is no doping gradient, this term will also be 0. So we are left with only this term. So del j by del x will be equivalent to del e by del x due to this. And finally, if we substitute del e by del x from here, that is minus qn, we will get tau equals to epsilon by q n mu. And q mu is sigma. Therefore, tau is epsilon by sigma. Okay. Next question. Right. Y and t. Okay. So as we saw, tau is epsilon by sigma, and sigma is nq mu. So since mu n is greater than mu p, therefore sigma n is greater than sigma p, or tau n is less than tau p. So n type will respond faster to electric field changes than p type. Okay. Next question. Okay. So the question is, what is the purpose of Scarpetta-Gummel method in semiconductor device modeling? So basically what this method does is, it helps to accurately capture the non-linear variations of carrier concentration between grid points. So let us see how. So I've taken the snapshot from the lecture video. Okay. So by finite difference methods, we can calculate, if we solve the Poisson equation, we can calculate the differences between the potential. And if potential is varying linearly between any 2 points, then how will the charge density vary? Will it also vary linearly? No, absolutely not. Since charge density is proportional to the exponential of potential. So what? What's your point? Yeah, how will it vary? That's what I'm asking. Okay. So this Scarpetta-Gummel method is a method that helps us to linearize, capture this non-linear variation of charge density. That's what we have taken. Capture the non-linear variation of the carrier concentration between the grid points. So how do we do it is, so So this is simply, you can say this is the current equation, J equals to E n mu E plus E d dn by dx. So what we are trying to do here is convert this dn by dx into d psi by dx, because d psi by dx we know we have already linearized it. D psi by dx from these finite element methods is psi I plus 1 minus psi I by delta x. This is d psi by dx from the finite difference methods. So dn by dx will be dn by d psi into d psi by dx, which is dn by d psi into this part. Now here what we have is, if I just rearrange this equation, this is what I get. And if I put this value of dn by dx, this value of dn by dx, if I substitute here, this is something what I will get. Now the final equation is dn by dx, sorry, dn by d psi minus n by vt equals to current upon ed into del x by psi I plus 1 minus psi I. Now this is a one-dimensional partial derivative, partial differential equation which can be solved. Whose solution is c e to the power ax plus b by a, and this is how we determine the charge density n. N is c e to the power psi by vt plus b by a, and coefficient c, b and a are found using boundary conditions. So this is a very broad summary of this method. So basically it is used to identify the variation in charge density when we know the variation in the potential. Is it clear? Okay. Next question is, what is the advantage of using central difference method over forward difference method? So answer is higher accuracy. So let's see what these methods are. So these methods are used to determine the derivatives, right? These methods are used in the simulators to find d psi by dx to solve the Poisson equation. So we use these finite difference methods to solve the d psi by dx in Poisson equation. So how it is solved is, if you see, this is the Taylor series expansion of f of x plus delta x. which is fx plus del f by del x into delta x plus some higher order terms. Now in forward difference, what happens is what we do is this fx plus delta x, we take this on left hand side minus f of x upon del x will give me del f by del x. So this is the forward difference method. In backward difference, what we can do is instead of writing fx plus delta x, we can write f x minus delta x is equals to f of x minus del f by del x into delta x, and again by resubstituting, taking this on LHS and this on RHS, we can get this. This is the backward difference method. This plus O delta x means plus some higher order terms with the of the uh, of the order of delta x. So at the end, what I'm doing, dividing by delta x, right? So when it is divided, all the rest of the terms are divided by delta x. The delta x square by delta x will become delta x. So there are some other higher order terms which have minimum power of delta x. Similarly, that is the case in backward difference method also. In central difference method, what we do is we find fx plus delta x using this Taylor's expansion. We also find fx minus delta x using its Taylor expansion, and then we subtract these two equations. Then we get this fx plus delta x minus fx minus delta x upon 2 delta x. This is the central difference method to find del f by del x. Now here if you see the terms that we are left with are del x cube by 2 delta x. So if we cancel the powers, the order we are left with del x square. So we are approximating more higher order terms here. So that's why this method is more accurate. Okay, is this clear? Okay. Next question. Okay, so the question is what characterizes the Newman boundary conditions in numerical methods? So if you look at the boundary conditions from the lecture, so there are two types of boundary condition. One is Dirichlet boundary condition, another is Newman boundary condition. In Dirichlet boundary condition, the function values at some boundaries are given. So that means if this is some your boundary of your function, here it is value 0, here it is value 1. These are Dirichlet boundary conditions. Whereas in Newman boundary conditions, instead of directly giving the function values at the boundaries, the derivative of the function is provided at the boundary. So it can tell us if the function is if the derivative is 0, that means the function would be constant at the boundaries. Or if the derivative is linear, that means function could be exponential at the quadratic at the boundary. So Newman boundary conditions gives the derivative of the function at the boundaries. So Answer to this will be B. Specifies the derivative of the function at the boundary. And the first one is distillate. Okay, next question. Yes. So let's say when any function you have is varying sharply in some range, you can have some uniform grid in the region where it is not varying very steeply, but when it starts to vary steeply, you can have a very closer grid to quantify it correctly. So we generally use these types of non-uniform grids while performing the device simulations. So it will be non-uniform grids. So okay, next one. Yes. What is the Einstein's relation? Right. dn upon mu n is kt by q, or dn equals to mu kt by q or mu vt. Okay. Next, we have yes, we have dp equals to mu p kt by q, and sigma is given. Sigma p equals to p q mu p, or mu p we can write sigma p upon p q. So this will become sigma p upon pq into kt by q. So sigma p is 1.28, p is 10 to the power 16, q is 1.6 into 10 to the power minus 19, kt by q is 0.026. This is the dp. If you solve this, you will get 20.8 centimeters square per second. Option A. This is clear. Next question. In semiconductors, the continuity equation is essential for the drift diffusion model because A. It ensures correct. It ensures conservation of charge. Continuity equation is dn upon del n by del t is 1 by q del j g minus r. So it ensures, it accounts for where all the carriers are coming from, which is conservation of charge. Okay. This is the last question I have for today. Mu1 is given as 1400 and diffusion coefficient dn is 36.4 centimeters square second. We have to find Vd, dn upon d minus Vt. So Vt will be 36.4 divided by 1400, which will be 0.0264. Okay, so this was the last question for today. If you have any doubts, you may ask, else we will close the session and we'll meet next week. Which concept do you want me to repeat? Okay, what are your doubts? So in semi-classical transport, what I would suggest is, okay, so the derivations are not important there. So if you see derivations are like very long, an exhaustive derivation. So don't worry about that. Those are not important. But the results are important. Try to see the conclusions and the assumptions behind uh, all those derivations. Those are important. But following the entire derivation is not important. Nobody will ask you that. Yeah. So just sure, sure. So semi-classical transport is uh, just take it. Uh, just try to derive the conclusions from every lecture. Don't go behind the derivations. That's fine. You can watch it at 2x, but just try to see what is the conclusion of that of uh, whatever is being taught. Don't go behind the derivation. Those derivations are not important. Nobody will ask you that.